All right, let's dive right in. We're going to tackle one of the absolute biggest hurdles in artificial intelligence. How do you teach an AI to solve a problem that's just astronomically huge? You know, the kind of problem where you could never, ever write down all the possibilities?
So, just to frame this, think about this for a second. How on earth does an AI master a game like Go? I mean, on the surface, it seems simple enough, right? But the sheer scale of it, it is absolutely mind-bending. You can't just feed it a list of the right moves for every situation, because there are more situations than we can possibly comprehend. That's the number. 10 to the power of 170. That's how many possible board positions there are in Go. I mean, just try to wrap your head around that. It's a number so colossal that it makes the number of atoms in the entire known universe look like a rounding error. So trying to create a simple list of answers isn't just hard, it is completely, fundamentally impossible.
And this brings us to what we can call the wall of infinity. It's this fundamental barrier that early AI research just slammed right into. How do you possibly solve a problem when the number of states you have to deal with is, for all intents and purposes, infinite?
You see, early AI, especially in reinforcement learning, tried to solve this with something called a lookup table. Just think of it like a giant cosmic address book. For every single state the game could be in, it would have an entry telling the AI, okay, being here is worth this much. Now this works okay for simple games, but for something like backgammon, that table is already massive. For Go, impossible. And for something like real-world robotics, well, the number of states is literally infinite.
So yeah, the whole table approach fails for two really big reasons. First, memory. You couldn't store a complete table for Go even if you used every single computer on the planet. And second, time. Even if you could somehow store it, it would take longer than the entire age of the universe for the AI to visit every single state just one time to learn its value. The whole approach just hits a brick wall.
This meant a huge, fundamental shift in thinking was needed. We had to move away from trying to create this giant table to memorize absolutely everything. The new approach, it was to create a smart map. Instead of memorizing, the AI needed to learn how to generalize and estimate.
And this smart map idea is the absolute key to everything. Now, the technical term for it is value function approximation, but honestly, thinking of it as map making is the perfect way to really get how it works.
So what is value function approximation? Well, it's the process of creating a compact, generalized model, our map, that estimates the value of different situations, instead of storing an exact value for every single one. It's like, instead of memorizing the precise location of every single grain of sand on a beach, you're creating a topographic map that just shows you the general shape of the dunes.
And what's so powerful about this is generalization, right? With a good map, you can stand on a hill and get a pretty good estimate of the altitude of a spot nearby you've never actually been to, just by looking at the contours around you. And that's exactly what the AI does. It learns the general shape of the problem so it can make really intelligent guesses about situations it has never ever seen before.
Okay, but how does an AI actually learn to draw this map? It's not like it can just look at the whole landscape at once. It has to learn from its own experience, one little step at a time.
You know, in a perfect world, like in something called supervised learning, the AI would have an oracle, basically a perfect teacher who knows all the right answers. For any situation, the oracle could just tell the AI, hey, the true value of this state is exactly 7.3. But of course, in the real world, and especially in reinforcement learning, that all-knowing oracle just doesn't exist.
And this is the core challenge, right? If there's no perfect teacher, no cheat sheet providing the right answer, how does the AI ever know if its map is any good? Where does that ground truth even come from?
Well, the AI has to create its own temporary right answers. We call them targets, from its own experience. And you can think of these as different kinds of survey data. A Monte Carlo target is like hiking an entire trail from start to finish and then noting the final elevation change. You get the real, true score, but you have to wait till the very end of the game. A TD target, that stands for temporal difference, is different. It's more like taking just one step, checking the immediate reward, and then just glancing at your own map to estimate the rest of the journey. It's way faster, but it's also relying on your map, which, might still be wrong.
So the AI uses this survey data to constantly update its map in a really simple four-step loop. First, it makes a prediction using its current map. Second, it takes a step in the game and gets some new survey data, a target. Third, it calculates the surprise. That's just the difference, the error, between its prediction and the new target. And finally, it nudges the contours of its map just a tiny bit to reduce that surprise in the future. And it does this over and over and over, millions of times, constantly refining its understanding of the landscape.
Okay, so having a map that tells you the value of different places, that's great for knowing the landscape. That's prediction. But the ultimate goal isn't just to know, it's to do. We need to use that map to get somewhere, to make decisions. This is the big leap from prediction to control.
And to make decisions, we need a really special kind of map. Not one that just shows the altitude of where you are, but one that shows you the value of heading north, south, east, or west from where you are. This is called an action value function, and it's the exact map the AI uses to choose its next move.
Let's make this concrete with a classic example, the mountain car problem. So you've got this underpowered car and it's stuck in a valley. It can't drive straight up the steep hill to the goal flag. The only way it can get out is to build up momentum by driving back and forth, rocking its way up.
This shows you exactly how that action map gets built. In the first few attempts, the car just kind of wiggles around randomly. Its map is totally flat and useless. But after a while, it accidentally discovers that rocking backward, literally moving away from the goal, is actually a really valuable action. Whoa! The map starts to form contours. Then, after a few hundred attempts, it masters the strategy, and its action map clearly shows this brilliant path to victory, guiding the car to build just the right momentum to reach the peak.
All right, now let's see how all these ideas scale up from a simple problem like mountain car to a truly world-changing result. This is where all the pieces, the smart map, learning from experience, and these action values really come together to do something incredible. So back in 2013, researchers at DeepMind combined all of these ideas with powerful deep neural networks to create what they called the Deep Q Network, or DQN. And then they just unleashed it on a whole suite of classic Atari 2600 games, feeding it absolutely nothing but the raw pixels on the screen and the score. That's it.
But here's the thing, just plugging a giant neural network into the learning process, it was super unstable. The AI would often just fail to learn anything at all, or it would spiral completely out of control. They needed a couple of brilliant engineering tricks to tame this thing and make it work reliably. The first trick was called experience replay. See, learning from one moment to the very next is a bit like trying to learn to drive by only looking at 1 second of road at a time. It's too correlated. So instead, the AI stores its experiences in a kind of memory bank and then learns by training on a random scrapbook of its past. This totally breaks up the correlations and makes learning way more stable. The second trick was fixed targets. If the AI is trying to update its map while using that same map as its reference, well, it's like chasing a moving goalpost. So instead, it learns by comparing its predictions to a stable, slightly older version of its own map. This gives it a solid, unmoving target to aim for.
And with those two innovations, the result was just incredible. This single DQN algorithm learned to play nearly 50 different games, and it achieved superhuman performance on many of them without being specifically programmed for any single one. It went from that wall of infinity we started with to a general, powerful game-playing AI.
So we started with a problem that seemed literally impossible, a state space larger than the known universe. And the solution wasn't to memorize every detail, but to learn how to generalize, to create a smart map. And if this approach can master the incredibly complex landscapes of games, it really begs the question, what other impossibly vast landscapes in science, robotics, or medicine can it learn to navigate next?